Hey, welcome. Today, we're diving into the hidden science that not only powers your phone, but also puts the shiny chrome on your car. It's really a tale of two chemical cells, one that makes power and one that uses it. But get this, they both run on the exact same principle.
So think about it. What could a plain old AA battery possibly have in common with the gleaming chrome bumper on a classic car? One creates energy and the other is, well, it's just shiny, right? The answer, as you're about to see, is all about the super-controlled movement of electrons.
But before we can get to batteries or chrome plating, we've got to go back to the very, very beginning. It all starts with this kind of hidden spark, this amazing thing that happens the exact moment a piece of metal touches a liquid.
And that thing is the world of electrochemistry. At its core, it's the science that connects the chemical world of atoms and molecules with the electrical world of current and voltage. It's all about reactions that either create a flow of electrons, which, is electricity, or use electricity to force a chemical reaction to happen.
So, where does this incredible connection even start? Well, like we said, it all kicks off with that hidden spark, this invisible but really powerful event that sets the stage for everything else.
And here it is. This is that spark. The very instant a metal rod touches a solution, a tiny separation of charge happens right there on the surface. Now, scientists have a fancy name for it, the Helmholtz double layer, but just think of it as positive and negative charges lining up in two perfect little rows. That separation creates voltage, an electrical potential. And that right there is the fundamental energy we can either tap into or have to work against.
Okay, so we've got this potential energy just sitting there. How do we actually use it? Well, let's meet the first character in our story, the galvanic cell. This is the one that makes power, and it's the hero inside pretty much everything, from your TV remote to a Tesla. And this is it. You probably know the galvanic cell by its everyday name, a battery. It's so cleverly designed to take a chemical reaction that wants to happen all by itself, we call that a spontaneous reaction, and it forces the electrons to take the long way around, through a wire. Think of it like a waterfall. The water wants to flow downhill anyway. We just put a turbine in its path to get some electricity out of it. So let's break down how it works. You've got two main players here. The anode, that's our negative terminal, which is the part that gives up electrons. Then you have the cathode, the positive terminal, which happily accepts them. Electrons flow from the anode to the cathode through the wire, and boom, you have current. But see that salt bridge in the middle? That's the real unsung hero. It lets ions move between the two sides to keep everything electrically balanced. Without it, the whole show would stop almost instantly.
Now, how on earth do you remember which is which? Well, here's a classic chemistry trick. Just remember ANOX and red cat. ANOX helps you remember that the anode is where oxidation happens. That's the loss of electrons, like you see with the zinc here. And red cat tells you that reduction happens at the cathode, and that's the gain of electrons, where copper ions turn into solid copper. Okay, so that's how we get power from chemistry. But what if the reaction we want doesn't want to happen on its own? What if we have to force it? Well, that brings us to the second character in our story, the electrolytic cell.
Exactly. What if you want to push that waterfall back uphill? A galvanic cell is all about harnessing a natural energy flow, but an electrolytic cell, that's all about using an outside power source to force a reaction that would absolutely never happen on its own.
And here's what that setup looks like. Notice the biggest difference right away? That power supply at the top. That's our pump. It's pushing the electrons where they really don't want to go naturally. This thing is the industrial workhorse that recharges your phone battery, puts that shiny finish on a car bumper, and purifies metals. So the critical point here is this. That power supply acts like an electron pump. It's literally pulling electrons away from one electrode and forcing them onto the other. This external muscle overcomes the natural tendency of the chemicals. In this diagram, for instance, it's causing chlorine and hydrogen gas to bubble up. We are actively converting electrical energy back into chemical energy and storing it in those new products.
All right, let's put them side by side and see the whole picture. We've got a cell that makes power and a cell that uses power. They have two totally different jobs, but both are governed by the exact same rules of oxidation and reduction.
So on the left, you've got the galvanic cell, our battery, just letting a spontaneous reaction run its course to give us a current. And on the right, the electrolytic cell, our little factory, using a power supply to force a non-spontaneous reaction to happen. One gives energy, the other takes it. Simple as that.
This table just makes the comparison crystal clear. The reaction? Spontaneous versus non-spontaneous.
the energy flow, producing versus consuming. But now, look at the last part. The charges are flipped. In a battery, the anode is negative. It's the source of the electrons. But in our factory cell, the anode is positive, because that external power supply is literally ripping electrons away from it. This is probably the most important difference to remember.
So, what's the big takeaway from all this? Electrochemistry isn't just some topic from science class. It's the fundamental bridge that connects the chemical energy stored in atoms to the electrical energy that powers our entire modern world. It is, at its heart, the science of energy conversion.
And that bridge is more important today than it's ever been. When you hear people talk about creating green hydrogen by splitting water, that's an electrolytic process. When they talk about building the next generation of incredible batteries for electric cars, that's a galvanic process. So the real question is, by mastering these two types of cells, what are we going to power next?